Hi guys, and welcome to this first video lecture on the biochemistry unit. We're starting off with chapter 2 on atoms and bonds. The big questions that you should know for this chapter are: what is matter? Where does it come from? How do atoms interact with each other? And more importantly, how do they lead to the emergence of things that we need in everyday life? So, the Big Bang Theory. This is a theory that states the universe was once a hot, dense mass, and the sudden, rapid expansion caused matter to go flying off in all directions, thus having an expanding universe. So, when we look at the matter that came flying out of this hot, dense mass, the smallest fundamental unit that we look at is the atom. There are approximately 120 different kinds of atoms. They are defined by the number of protons that they have inside their nucleus. We see that there are also a group of electrons circulating around the nucleus, but it's not actually true to say circulating around. We frequently think of electrons as existing in an orbit, and although that is kind of true, that they do exist outwards from the nucleus and not directly on the nucleus, they don't orbit and circle around like a moon does or a planet does to a star. Essentially, we don't actually know where an electron is, just that it occupies the space outside of the nucleus and that it occupies space at various distances from the nucleus. The more energy that an atom has, the further away the electrons are, and the less energy they have, the closer the electrons are to the nucleus. Biology is made up of four major elements, that is carbon, hydrogen, oxygen, and nitrogen. They make up 96.3% of our body's mass. Some of the more minor elements, such as calcium, potassium, and sodium, were explored in our last unit regarding cell signaling, and so just because they're not major components in the human body doesn't mean they don't play very significant roles. In fact, even some of the trace elements, some of them that you've probably never heard of, such as Mo, is a very significant player in the human body. Some examples is that it's a bad scene if you don't get your elements. So here you can see some plants. Each of these plants have a different nutrient deficiency, and you can see that they're affected physically quite a bit by it. Over here you see a woman who has a goiter, which is an inflammation of the thyroid gland in the neck, and this usually comes from a lack of iodine in the diet. So you could see that even these trace nutrients are very important for humans. Now, we talked a little bit about energy in atoms. Essentially, what's really important for you to know here is that as energy gets absorbed into the atom, the electrons jump further away, and as the atoms lose energy, the electrons get closer together. So, how do atoms interact with each other? Well, there's two major kinds of bonds that hold atoms together. The first is ionic bonds that we'll look at, and this is where an electron really gets shared from one to another, or gets transferred, not sharing, that gets transferred. Ionic bonds are when electrons get transferred from one to another. These are kind of boring because there's not very many possible combinations that can come from this. Look at the example of sodium and chlorine. Essentially, one sodium atom has an extra electron and one chlorine atom is missing an electron. And the sodium atom will essentially give the chlorine atom and its electron, and they will stay together because of this attraction. So, a slightly neater example are covalent bonds, and this is where we get all sorts of different possibilities, because in this case, rather than transferring electrons over, some of these electrons are actually covalent bonds is a sharing of electrons, and these are really neat because there's really an infinite combination that we can have here, and all of the important biological molecules are really covalently bonded. Now, take a look here at the atoms are sharing with each other, and 2 oxygen atoms are sharing electrons with each other. Now these oxygen atoms are actually sharing 2 electrons with each other, and so then we represent this usually with a double bond. You can see water, there are 3 different molecules that are sharing electrons, 2 hydrogens and 1 oxygen. In the case of methane, you've got 4 hydrogens and a single carbon sharing with each other. So not all bonds are created equal. Essentially, when electrons are shared in a covalent bond, it's not always an equal distribution of the charge in the molecule. In this case, you can see a hydrogen molecule has a slightly positive charge and an oxygen molecule has a slightly negative charge. This is how water molecules stay bonded to each other, and this is why frequently water is found together in pools versus found in single atoms. So we call these hydrogen bonds, and the strongest attractions are between those molecules that are the most polar. In other words, the ones that are the most magnetic or have the highest charge will have the highest source of attraction to each other. Also take a look in your text for van der Waals attractions, and you can see why a gecko can climb a wall. Now, we talked about this again, that bonds determine shape. This is a very important concept in biology. Structure and function are always going to be related to each other. We can see here that an endorphin molecule binds to an endorphin receptor and has a cellular response that makes you happy. And morphine mimics this. And so by introducing morphine into our body, we are tricking ourselves into thinking that endorphin has been released, and our endorphin receptors then create a cellular response that make us happy. Now, all chemical reactions result in the breaking and forming of bonds, and this means energy gets released or is used. Now, just because energy is being used up or being given off, it doesn't mean it's actually being lost in the universe. It just means it's changing form or changing shape. Therefore, anytime there's a chemical reaction, the mass, energy, and charge are always conserved within a system. So, when a compound is formed, it has very different properties than the elements that made it up. Sodium is explosive metal. It reacts with pretty much anything, including water. Chlorine is a toxic gas that we would not want to breathe in, but put it together and it makes up the delicious table salt. Now, radioactivity. What happens when an atom has an unstable nuclei? Well, essentially what that means is that there is an odd number of neutrons in the nucleus. Certain elements have various numbers of neutrons in its nucleus, and we call these isotopes. Now, some isotopes are unstable, meaning if they exist with so many neutrons in its nucleus, it wants to give them off and it fires them off. And this emission of high energy particles essentially will keep happening until it reaches a stable form. But in the meantime, while these high energy particles are being emitted off, they can react with other atoms, cause great damage, and cause atoms to change into different types of atoms. So an element will act like a different element. So you can imagine if we took oxygen in our body and we turned it into a different element, that would obviously have some harmful effects. Now we can also use this as a molecular tag. So one of the nice things about isotopes is if we are able to create a radioactive yet harmless compound, or atom, I should say, and we were to put this into the body, we could trace exactly where certain things are happening in the body. And this is one thing that we do with PET scans, as we talked about during our reading, that if we're able to inject a radioactive isotope into our body and it goes to a certain area, we're able to find out where exactly that cancerous throat tissue is. So, if you have any questions, get ready to ask me in class tomorrow when I see you guys. Hopefully, by the end of this lecture, you're able to answer the essential questions that you kind of see at the end of your textbook reading. Also, make sure to get those questions done for tomorrow, and we'll do a few activities with water and get ready for the Chapter 3 lecture.